Hi, it's time for another math easy solution. To discuss further into the Tengri 137, the online cryptic puzzle or series of puzzles, and now look at Odin's triple horn again and revisit it, and this time show a visual representation of it, and also the basis for which I believe it was formed. So in my last video I went over the Tengri 137 cryptic online quote alien puzzle and discussed most perfect magic squares and how they are used to make the Odin's triple horn. So make sure to watch my earlier video to learn more. First off, I want to point out a few mistakes I made in that video, but nonetheless the final result remains that the Odin's triple horn is likely the work of a very talented and possibly bored mathematician. So recall that the Tengri triple horn are a group of, is a group of 6 most perfect magic squares with the magic constant of 666. And basically contains numbers between 119 to 214 in series, so it fills in every single number between these and no duplicates or no missing numbers. And are grouped to look like the 3 drinking horns emblem of the Norse god Odin. So again, make sure to watch my early video. Here's from Tengri137wikia.com. Here's that document with this this cryptic writing, and here is the Odin's triple horn, and these are the 6 perfect magic squares. Every single row here adds up to 666, etc. So first off, I want to go over a few mistakes I made in my last video. So if you go to, well, I have the link here to my video, but if you go to the 28-minute and 5-second mark, and here's the part where I made some mistakes. So in this, I said, notice that we have even more matrix transforms, and I have these ones listed here where I looked at this. If you look at, if this is A, then this is going to be negative A, and I have A, negative A, etc. And also I have, if you have B here, negative B is over there, so B, negative B. So I thought this is all you need, and this is actually not correct transform, because I forgot that what you also need is, well, in this case here, if this is A as well. Then you have negative A here. So this is, instead of G, this is going to be negative A. And then instead of G here, this is just A. So you have A, negative A, and A. So we'll get something like that. And in fact, it is for all of them here. If you have 12 here, then you have the other pattern of where this is 12, negative 12, and then negative 12 there. So notice the pattern like that. Same with 34s like this, etc. And in fact, every row needs to add up to 0, so I forgot to include that as well. And also I wrote that this means that we can go from a distinct 4x4 pan magic square to any of the other ones. In fact, this is wrong. We can't go to any. We can only go to most of them. I'll show you that in a bit. So note that this matrix transform is actually inaccurate. A corrected transform is shown below. So here I updated that. So as you can see, the 28, 28, 28, 28 like that. And also the 12s, and I have the 34s, there's the 18s, etc. So when I added a correction in that Excel file, so if you go to see it in that video, the Excel file is updated. So the matrix transform is actually as shown above, which is now fixed. This transform only works for Tengri squares 1, 3, 4, 5. For square 2 and 6, we first need to rotate any other Tengri square. So watch my video, Odin Horror Visual Representation. That's this video, which I explain this matrix in more detail. So this new updated matrix transform, in fact, only works to obtain Tengri squares 1, 3, 4, 5. For Tengri squares 2 and 6, again, as shown in my last video, we do in fact need to rotate any other Tengri square clockwise, 90 degrees. And I've updated that Excel sheet that I used in that video, so check it out. So now let's revisit that Odin's triple horn. So recall that there are 3 distinct 4x4 most perfect pan-diagonal, quote, diabolical magic squares. If you go to Wikipedia, it shows these pan-diagonal magic squares like this. And basically the smallest non-trivial pan-diagonal magic squares consist of numbers 4x4 squares, and you have here's the smallest ones. Yeah, so there are only 3 distinct 4x4 pan-diagonal magic squares, namely A above, then you have B and C. So you have these 3 distinct ones like that. In 4x4 pan magic squares, the magic sum of a constant of 34. They all fulfill the further requirement of a 4x4 most perfect magic square, as does the Tengri squares. So in response to someone that asked in my last video, these distinct 4x4 squares don't mean we get distinct Odin triple horns. This just means that they're the simplest form that they can be in, which is the numbers from 1 to 16. Yeah, well, so without rotation. If you rotate them, you're not really, it's nothing unique. If you move this, if you rotate it across, you're just going to get, well, it's the same thing. It's like, you can just look at it sideways. It's different. So without rotation, this just means that we can in fact obtain the triples horn from any of these 4x4 squares, which I will show soon. This just means, again, when you play around with it, add matrix transforms, the simplest you'll get is these 3. They don't mean that they're distinct in the fact that you'll get distinct results. It's just that they are the simplest that you can transform any of these most perfect squares to. And again, I'll show that in the Excel file at the end of this video. So to understand the Odin horn in more detail, I first made my own MES square, which is again simply just a distinct A square plus 158 on all values. Then graph the numbers in comparison with the Tengri squares. So if we distinct square A, here's that from the Wikipedia one, add 158. So this one is a 34 magic number. And then you get here, which is in fact a 666 mark of the beast magic number, same as all these Tengri squares. And this goes from 159 and then I believe it goes to 174. So minimum, maximum, like that. And this is in full series. And I basically put all these together, all the Tengri squares, and then I graph them from the smallest to largest. So you have 131 all the way to 202, you have my square 159, again 174. And notice what we notice here is that from minimum to maximum, we have everything in groups in 4s. Tengri square 1, so 131 to 134, 151, 154, etc., 179, like this. Everything's in groups of 4. In fact, mine is in also groups of 4 like that, but mine's also full continuous 16. So it's groups of 4 of mine, but it's also group of 16 like that. And same thing for all of them. Tengri square 3, you have 4 in series, 4, so everything's in 4s, and they have to be for symmetry in order to be most perfect. And then Tengri square 6, what we actually have is a pair of 4 as well as a pair of 8 here. So this one is from 163 to 170, same thing as 4s, or you can go a full 8 like that. So in fact, only the Tengri square 6 has an 8 pair, but again, 8 pairs still, just divided by 2 is just 2 4s. And same thing for all these 5 and 4s are all groups in 4s. So now what I did was I graphed this to visually see what the Tengri squares are all about. So the middle one is my squares. This is MES like that. This is in 16 pair. This is the Tengri square 6, has an 8, but then also at the corners are there. These are 4s and these are 4s. And these all add up to 16. So in fact, when you look at this visually, this is from 119 to 214. All the Tengri squares is, well, it just takes this middle square like this, and then everything needs to be symmetric. That's just the basis of all these most perfect stuff. Is all symmetry. Doesn't matter how you rotate them, transform them. It's going to be the exact same perfect sum. So all that it does then is the basis of this whole Tengri square puzzle for the Odin triple horn is, well, you take, for example, you start off where my square is, then you take 4 of these in the outer ones, and 4 of the smallest and 4 of the largest numbers, and you just transform them, or you just move them across like this. And in fact, this is just the basis of this whole thing. And even when you go back to that matrix transform, I'll go in more detail, but if you look at this, if you add here, whatever you add to this one, then you're going to have to subtract, or this one subtract, you have to add. And in fact, these are the smallest and largest numbers for when you look at mine over here. So where's this? So this is the smallest number, and then if you go opposite like that. So if we subtract by whatever number, we have to add to the largest number. So that's how we can basically see this. So if we subtract 4 of these to get all the way to somewhere around 119 to 123, and then we have to add to the largest ones to get over here. So notice the symmetry. We could also move this over here. Actually, yeah, I forgot. There's an 8 over there as well. Let's front an 8 like that. Yeah, so this one's Tengri square 4. This was actually a full 8 like that. Okay, so that just splits it in half. You can move 4x4s all the way across there. So as you can see, all it is just symmetry. You're just moving things around. So yeah, let's look at that 4 again. So this one is actually, yeah, this one is an 8. Yeah, all the way to 4, 6. So this one is splitting it down the middle and moving it across, or just moving again. It's still in 4s. So everything, the 4s still remain. So that's pretty much it. You just visually move things around. So as can be seen, there's a distinct pattern. My square is in the center, while the Tengri squares are simply transformed so that the groups of 4s are separated across the spectrum. This, in fact, is the basis behind the Tengri squares. To obtain exact Odin horn, the exact one, we can start with any distinct 4x4 square, add 158 to it, and then apply what I like to call the magic zero matrix transformation, which is in fact the correct matrix the corrected transformation from my last video. So here it is at A, then you have this negative A across, then you have A, negative A, like that, where then you have A, B, C, D. So where D is equal to 0 minus the sum A plus B plus C, because every row, everything needs to add up to 0. So A plus B plus C plus D must equal to 0, so we get a 0 sum like that. Across everywhere needs to be 0. And in fact, this transformation, makes everything, it's just a cool 0 one, like that. And this is B's, and etc. So this matrix transformation is just an example of a magic square with a magic constant of 0. This means that we can add this to any 4x4 square to change the values in the square, but keep the overall magic constant. Applying this matrix to my MES square will obtain the Tengri squares 1, 3, 4, 5. To get Tengri square 2 and 6, we just rotate any of the Tengri squares clockwise 90 degrees, and then apply the matrix 4 transformation from my last video, and I'll show this all in a bit. You can play around with this in the Excel sheet that I made. I'll further look into these original distinct squares, how they're formed, so stay tuned. Actually, I'll read this part in the end. So let's just go to the new Excel sheet that I made. So here's another one. I put the link in the description below, and you can download it and view it. So yeah, here is the Excel sheet, and initially I made here's my comparison ones where I compared all 6 Tengri squares with my MES perfect square like that, which is just this distinct square plus 16, etc. Then I just made this little table. Here's the graph. You can play around with it. Yeah, now let's just go to the magic matrix manipulator that I made. So here's a cool website that I made. I mean Excel sheet, not website. So if you go here, notice what we have. So what we have here is distinct square A, and I have all these 3 distinct squares across there. And now here's the calculation count, just to show you I have 44 of these. I believe there's like 86 total, but as you can see, the sum here is 34. You do a bunch of other sums. This is going to be 34, so this is the most perfect magic square here. So this is distinct A. If we add 158 to it, to every single one, so this is every row, every cell here is add 158, we get the 666. If you add 157, you get 662. So then you could just play around with it. It goes up by 4. Every time you add 1, you go up to 4. So yeah, as you can see, if you add 1 here, because all we're doing, because this one's 34, if we add 1 to every cell, then the sum is going to be, well, you're going to obviously add 4 to them, 38, etc., then 42, and then you go all the way to 160, etc. We got to subtract. That's 174, so we got to subtract 2 of these, 158. We get 666. So that's my square. Then we add. This amazing magic zero matrix, again where D is 0, and all we need to do is update 3 of these A, B, C, because D is a calculation, it's just the summation 0 minus the whole summation, so everything adds up to 0. So then if you just highlight this needs to add up, to 0. As you can see here, sum is 0 in this little thing like that. And so now what we get, so if we add these numbers, I'm just going to add 0 here, 0, 0. We get a 0. So then we just check the difference here and see what we get. And notice the difference here from my original one is this 28, this negative 28, 34, 18. And we can just put, well, negative 28, 34, 18. Whoops. Is that what we get? Okay, no, it was actually negative 18. So this is negative 18. And yeah, we get differences 0, 0. This is just difference between the square above, just to double check if it's right. Just subtract them. Yeah, so this is the exact same one. So we got the Tengri square 1 just by just manipulating these numbers. So I need this ABC right here, and as you can see, this 159 is the lowest, because number was 1 to 16 like that. The 159 is the lowest number. You subtract 28 from it. What that means is we have to increase this highest number, 174. So again, as shown in the graph, we are separating the smallest and largest, and goes on for the second largest and second smallest as well, and that just happens here. So we get 131 here, but then we add we add 28 to the 174 to get 202. So we get Tengri square 1, and we can do this on and on. So we can do this to get the Tengri square 3 and 4. I'll do one more. Also, let's go to 5 right here. So 5, let's see, this one is -4, so we got to subtract. This is going to be -32. And 0, so then this is a 4, so this is going to be a 38. And there's a 4 and -4, so we got to go this one -14, and then this is a -4. Actually, no, that's it. Yeah, Tengri 5, as you can see, this is a perfect one. Difference is all zeros, so what we get is this. So we can do this for all 1 to 5. To get the Tengri square 2 and 6, the difference is we need to rotate it. So yeah, if we try to get these Tengri squares, here's the difference. Let's just try to get these. So I'll put these to quickly do it. Put 0, 0. Let's see what these numbers are. So Tengri square 2, the difference 38, 18, -2. Let's just put those in. 38, what is 28, -18, if I get those numbers right. Actually, whoops, it's actually 38, 18, -21. And then we get this pattern like this. So we can't get it from that matrix alone. What we can do is, all we need to do is get any of these Tengri squares. So let's just get these. So here I've went backwards like this, put a y. Yeah, here, so I just added those numbers again to get the Tengri square 5, and then what I've done over here, so now to obtain Tengri squares 2 and 6, we could rotate any of the above Tengri squares, and here is the square x. I just put square x here, so that I just put that exact same one here. Now if we rotate it, we get this value, and now we can apply the matrix transform over here. This is number 4 from my last video. So if we plus 0, we get that same thing. So notice this pattern here. Again, this is a 0 sum here. If you sum it, 0. So -1 plus 1, 0 plus -1 plus 1 is 0. So this is also a 0 matrix. And now we can just apply this one. This one's going to be, well, negative. Let's see what the difference, what the thing is going to be. So you can see the difference. This one is in 8s. So we could just go with 8 times. And now we get the Tengri square 2. This is just the difference from above. And there's our Tengri square 2. So when we add that, we have 197, there's 186, 186, etc. And we can do the same thing to get the Tengri square 6. And also, it doesn't matter which square we use. So if we do, let's say, the distinct B, just copy this here. So we copy that. Our 158, because it's still 1 to 16. Now we're just adding different stuff. So let's get, there was a Tengri square here. This one's -4 and 6. So we have to subtract. This is going to be 34. This is going to be -20. Actually, whoops, it's not -20. This one is, yeah, this one is actually at 12 there. It was actually supposed to be, this one's -8. I went up the wrong way. So when we add these ones, we get our Tengri square 5 over here. And then again, we can just rotate it and then apply, yeah, the same thing, 8 times matrix 4. And then we get our Tengri square 2. And we can do the exact same thing for Tengri square 6. We can get Tengri square 1, 3, 4, etc. And you can see the pattern here. This one here is, yeah, this one is pretty much the exact same matrix transform here. But the thing is, we just needed to rotate this all the way across here. So as you can see, this 205 goes to here. And then this, I'll just write this down. So 205 is over here because it rotates across. And then the 127 rotates across here. And there it is. Yeah, this one's rotating across. And likewise, that's all it is. You just rotate it around. And this is, again, as explained in my last video, where Tengri squares 2 and 6 are just rotations of the 1, 3, 4, 5. So yeah, that's pretty much it. You just apply these matrix transforms and you get it. And yeah, that's all for today. So again, I will look further into these original distinct squares, how they're formed, so stay tuned, because that's pretty cool, and see if I can derive them. Also, research into the rest of the mathematics involved in Tengri 137 puzzles, because regardless of whether they are a hoax or from aliens, they're very fun and interesting to look into, so stay tuned for what I discover. Anyways, that is all for today. Hopefully you'll learn from this yeah, pretty extensive video on these Tengri magic squares. I just wanted to go show them visually, and again, I can't stress this enough, you can just visually see it's just a pattern. So you just move this 4 here. When you move the 4, you automatically have to move these to obtain a magic square. There needs to be a symmetry. There's a symmetry all through everything is a mirror image from the very center. So this is just mirror. Whether it's 8 across and then 8 left here, or you have a separation like somewhere, for example, this one here, which is the Tengri square 3, etc. There's 4 and 4. I'll draw a better one. So if you have 4, 4, like that, that's all the way across here. And notice the exact symmetry. So this is all Tengri, yeah, all of this Odin triple horn is just using symmetry of most perfect squares, and they need to be symmetric. Need to be, yeah, symmetric in order to be most perfect. Anyways, that's all for today. Hopefully you learned, and yeah, like always, you can download these exact notes in the link below, as well as the Excel file. Everything's in the description below. So anyways, thanks for watching, and stay tuned for another math easy solution.